Hello, welcome. I'm very pleased to introduce Francis Rengers, who is a Mendenhall postdoctoral fellow at the USGS in Golden, and he works on understanding debris flow initiation after wildfires. He received his bachelor's in geology from West Virginia University and worked as a consultant with Engineering and Hydrosystems, Inc. He then completed a PhD in geomorphology at the University of Colorado at Boulder. So please welcome Francis to UNAVCO. Thank you.
Good. All right. Well, thanks for having me here, guys. I have definitely spent a lot of time here at UNAVCO getting my research right. So it's kind of nice to show you what I've been doing. Where are we at? There we go. Okay. So I just want to start by acknowledging lots of people. In particular, UNAVCO has been really instrumental in the work that I did for my PhD, as well as some folks from the broader community that were really helpful with software, and my colleagues at the USGS, and of course, the National Science Foundation. So what I'm going to concentrate on today are two case studies that I worked on. First was post-wildfire erosion, and the second case study is gully headcut erosion. And I'm going to probably emphasize the change detection and uncertainty methods in particular here, because I have a feeling that's the kind of stuff that you guys are interested in. So first, let me tell you about the 4 Mile Canyon site. This was a wildfire that burned from September 6th to 16th, 2010. Probably a lot of you, if you were in Boulder, you probably saw it and remember it. So what we were interested in doing is using repeat terrestrial LiDAR scanning to just do a small section of the watershed, starting at the top of a ridge and moving down about 150 meters. So in all, we did 5 scans. We were there. The most important thing is that we were there October 7th, so about 3 weeks after the fire was contained. That was the first scan, and Sarah and Brendan did that one. And then they came back just a couple weeks later after the first small rain event, and then did it again. And so we did 3 more subsequently. This is what my data look like. This isn't all the data, because it's really hard to render that into a movie that plays. It's not humongous, but it's some of the data. One of the things you'll notice immediately is all the trees. That ended up being probably the biggest challenge of this kind of environment, mapping the ground surface. But you still see that we get pretty good views of the ground, even though there are shadow issues from the trees. And again, this isn't all the points, so some of those shadows that you're seeing are actually filled in with points. So the way that I went about measuring erosional change with this LiDAR data set was to do a digital elevation, DEM to DEM comparison. And so basically the procedure I went to get there was, first I had to get rid of all those trees, or at least a large portion of the tree. So to do that, I used TerraScan, which is a software typically used with airborne LiDAR data sets. It's really expensive. It's like $10,000 a year. So it was cheaper for me to fly to Arizona and spend a week there than to get a license. So Steve DeLong helped me out with that. Then once I had a point cloud without some of that vegetation, I created a 10 triangular irregular network, and then interpolated that to a digital elevation model. And this is sort of a technical note, but I think you guys might be interested. I spent a lot of time thinking about what the right cell size is for a DEM with this kind of data. I ended up choosing a size of 15 centimeters, which is a little coarse in some areas. You could certainly use a cell size of 2 centimeters in a lot of places. But I'll show you the point density map, and you'll see why I kind of decided on that intermediate value. So this is the point density map, which I don't know if you've looked at one of these before, but it's really interesting how much, the point density is clustered right around the scan position. And so it ended up that because of that high variety in point density, it made the most sense for me to use 15 centimeters. That kind of maximized the cells that weren't just based on a single point value. So let me show you what the DEM actually looked like in detail. This is one of the 5 scans, the very first one, in fact. And if you look at that inset, figure A, you can see we get pretty good detail on fallen trees, and the little pock marks that you see all over the DEM are actually stumps. So that's from the digital deforestation that I did, removing the trees. The trees are still there in real life, but they're not there in the DEM anymore. And probably some of you have seen things like B and C before. They're not the photos, but they're the points colored with the RGB values from the scanner. So I always like looking at those. It's amazing. They really look like photos because of the high detail. So the next thing that I went down was uncertainty. And so for this, the approach that I took was a spatially variable uncertainty analysis. And the reason I did that is because there are areas that are very flat where you get a pretty good signal, and there are areas that are pretty rough or high slope where maybe you're a little bit uncertain on the point, actual point elevation values. So to do spatially variable uncertainty, I used the geomorphic change detection tool that Joe Wheaton created. He's from Utah State. And I set a range of my uncertainty. So my level of detection, that's the level at which I say, okay, when I subtract 2 DEMs from different time periods, where my level of detection is the level at which I believe the change. So my minimum level of detection is 0.5 centimeter. So any difference that's less than 0.5 centimeter, I say, well, that's within my error. I can't actually say that that's true change. But the level of detection ranged up to 2 centimeters in some places because I saw that in the more uncertain areas it could get that high. And to apply this spatially variable level of detection, I had to build what's called a fuzzy inference system. And I used 3 parameters. So the fuzzy inference system sort of bends pixels with uncertainty. So you have a low, medium, and high. And you can interpolate in between low, medium, and high. So areas that have the highest uncertainty are areas with high roughness, very high slope, and low point density. So a good way to think about that is if you went out and scanned a parking lot, that would have a low roughness, low slope, and a very high point density. But if you scan like a rocky slope that's really steep, you're going to have some issues with occluding areas and shadows, and so you end up having a high point density in those areas. So I want to show you what this looks like when you apply uncertainty versus when you don't apply any uncertainty. So on your left, there's a subtraction from the first scan and the last scan, and there's no uncertainty partitioning there. And on the right-hand side, there's a spatially variable uncertainty. So a few things that you might notice. And first, let me tell you that the red colors indicate erosion, blue colors indicate deposition, and the white is no change or less than my level of detection. So it's pretty obvious that when you don't apply any kind of uncertainty, you see a lot of change everywhere. So what's believable change ends up being what you base your level of detection on. But once I apply my spatially variable uncertainty, I still see change in the areas where I kind of think there might be change. So at the top of the screen, that's you see a channel that's forming. So water is actually flowing up that way. And so you see a lot of erosion in the channel, as you might expect. And then you also see erosion at the top of the slope. And one thing that people always point out and kind of get worried about is at this top of the slope, you sort of see a radial pattern where you have this red erosion, this radial. If you notice, that's largely absent in the no uncertainty area difference. And that radial pattern, what that is those are shadows created from trees, and there's very low point density in that shadowy area. So when your uncertainty is based on point density, then changes up to 2 centimeters, I go, I can't really say if that's change or not. So that's why you start to get that radial striping. And there's also, you can see underneath the scanner, it's kind of obvious the sort of circles where the scanner was. Those areas, there's not very great, point data. And so those are masked out pretty well with the spatially variable uncertainty. And they're just really weird in the area without any uncertainty. So a couple of the challenges that I faced and you guys face all the time are the trees. So again, here's a look at the top of the area, and you can see what I'm talking about. That radial pattern is from tree shadows. It's a little unfortunate when you do the difference that it comes out radially like that, because that also looks like a misalignment. But you can kind of see here the data structure itself has that radial pattern in it. And so that kind of shows up in the triangular irregular network. And that's what it Okay, I'm back. All right, sorry. So so this is what it looks like. Ooh, that's a little loud. This is what the area looks like when you look at when you apply that spatially variable uncertainty. You end up getting these weird stripes from the trees, but it's a function of the underlying data. It's not a misalignment issue. That's just where the data are dense versus where they're not dense. There are also environmental challenges of doing this. So this is a site when it was raining, and it just so happened that one of the scans that we did is actually Marianne and I were out on the site, and we had one of the highest rainstorms on the history after the burn on the site. So we just finished scanning the bottom half of the watershed, and the skies opened up. And so essentially, since we're trying to measure change after a wildfire and this driven by rainfall, we basically only had a bottom half of the data set, so that kind of interrupted the continuity. So that's just one of the challenges of doing it. Let me show you some of the results and some of the things we actually learned from this. So let's just take a look at a cross-section. We're going to just focus in on this cross-section here. So the very top of the screen, what you can see is the first 2 scans, that cross-section, and there was a little rainstorm, but essentially pretty much nothing happened at that cross-section. And then after the first thunderstorms, so there were a couple big thunderstorms, we get almost a 20-centimeter drop in erosion. So there was sediment in the channel that got eroded. Interestingly, the next big thunderstorm that was equivalent in size to the earlier thunderstorms didn't cause nearly as much channel erosion. And then when we come to the final scan, that was we see a little bit of erosion, but by and large, the most erosion occurred on the site after the fire, after the first really big thunderstorms. So a lot of erosion, and then not as much happened. And if we look at this on more of a spatial scale, so time 1 is the first 2 scans down to time 4, which is the last 2 scans. And what I have up there is the maximum rainfall intensity that we measured on the site. So what you see is at time 2, after a really high rain event, 70 millimeters an hour, a lot of channelized erosion. And then time 3, we have another pretty high rain event, 50 millimeters an hour, very capable of moving and eroding a lot of sediment. Not much happened. It was very spotty. It was, very patchy, we like to say. And then there wasn't the next rain event wasn't very big. So this spatial understanding of erosion kind of led us down this track to think about what's actually happening on the site. So what I want to show you is some initial pictures of the field site and then after the first thunderstorm. So the yellow arrows in this picture indicate rocks that are going to be the same in the next photo. So you can kind of use those yellow arrows. We're taking a photo at a flume at the bottom of the site. We're looking uphill. So you'll see this flume in the next photo. The position is not exactly the same place, but it's pretty close. Okay, so I'm just going to flip back and forth between these a couple of times so you can start to see the difference. And what I hope you notice is that in the second picture after the first thunderstorms, a lot of cobbles and boulders were uncovered, or exhumed. So there were cobbles and boulders in the soil itself, and those things, once they were eroded, the finer soil material on top of them was eroded. That's what was left, and so that created essentially an armor on the surface, and it wasn't just in this channel. So we're looking up a channel, but you can see on the hill slope too. There's just a lot of exposed large material. So what I tried to do is map how this roughness changed over time. So what you're looking at is a graph of cumulative roughness. So it goes from 0 to 1 on the y-axis, and the roughness height is in meters here. And the different lines indicate different scans. So interestingly, as you can see, after the first thunderstorms, there's this big jump in roughness. Overall, in both the channels and on the hill slopes, the roughness increased by about 5 centimeters. So you're exposing this rough material. And then the next 2 scans, we didn't see any change in that. And that's essentially because it's a lot harder then to move that material. So some of the conclusions here from this first case study is that with terrestrial LiDAR, we were able to quantify and contextualize things. We could see things like obvious channel erosion, which would probably make sense and you could visualize in the field going out there. But we also saw less obvious changes. We saw shallow hill slope erosion on the order of a couple centimeters. And one of the things I learned was that 1 centimeter over a large area ends up being a lot of material. So it's difficult to see in the field, but I'm pretty confident that when we apply our uncertainty, the changes that we end up saying, okay, we think this happened, we can be pretty confident in that actually happening. We're also able to quantify interesting watershed properties like roughness. This kind of hard and it's a tricky thing to do. I'm not sure if you can really do that without something like LiDAR. And the overall point of that we learned from the wildfire erosion stuff was that we see this hysteresis in erosion and then armoring, and then you can have a similar erosional driver of rainfall, but you just don't get as much erosion afterwards because the landscape has fundamentally changed. Okay, so now I want to shift gears, take you to my second case study. So this is out on the plains. So West Bijou Creek, about 30 miles east of Denver. And if you look in the shaded relief here, this map, this is an airborne LiDAR data set. You can see this interesting pattern where there's the Great Plains basically off on the east side, and then on the west side there's West Bijou Creek, which is incised into the plains about 100 meters, and it serves as a trunk stream, and so there are all these gullies that cut down to it. So in the middle of the Great Plains, there's some pretty interesting topography, and in particular, what I was interested in is things like you see in that photo C, which is a head cut. These head cuts move pretty quickly from year to year, and I kind of wanted to know how much they were moving and what may be causing that. And this research actually just got published in ESPL journal, or Surface Processing Landforms. So this is the head cut that we're interested in, and during the summer, there's water that runs over and creates erosion. And I'll just show you this video of winter erosion. So what you'll see is snow melting in, and you'll see two blocks fall. Those blocks fall, and then it's running backwards, so you can see them go back up. So I'll let that run one more time so you can actually see it. So there the blocks have fallen. So snowmelt and water runoff are two things that cause erosion of this head cut. So in order to look at it, we got this intrepid team that would come out. Rain or storm. Actually, the funny thing about the lightning was I was there alone, and I just said, I wish Dave Phillips was here. And then lightning bolt, and he walked up. It was weird. But anyway, that's the recess students, and they helped out. The recess, I've taken, there have been several recess crews. I think that this site, West Bijou Creek, has seen a lot of the early instrumentation and testing of LiDAR in general. So at one point, I'm not sure if it's true now, but at one point it was really sort of the test area for a lot of terrestrial LiDAR stuff. So over a period of 3 years, we did 10 surveys on this head cut. And I'll just give you a small video sense of what this looks like. So this is one of the point clouds. And what you can kind of see is there's just really good detail on the actual surface. So we got very high resolution detail everywhere, and we, thank God, didn't have things like trees to deal with here. So my approach to change detection was actually quite different at this site. Here, I used a point cloud to point cloud difference, primarily because surface geometry for this highly curved landform, so it was curved in several directions, it's really impossible to do a true DM difference on something like that. So I went to a point cloud to point cloud difference. I also use a spatially uniform approach to uncertainty, because unlike a watershed with like different slopes and rocky and not rocky areas, this was pretty uniform everywhere. So there wasn't really a good reason to have a spatially distributed uncertainty. So the uncertainty here was pretty easy. It was just a GPS scanner and registration error that kind of set the level of uncertainty I used. And I just thought I'd throw this in just to show you. I know you guys play around with different tools, so I played around and I used Dimitri Log's Canupo method for removing the grass, and I was really impressed that it got grass pretty well. You can see in this difference. So I used that whenever the grass was an issue, but in general, there really wasn't even that much grass hanging over the head cut, which made it kind of a nice thing to scan. Okay, so let me show you the result of what we did. So at the top, you're looking at a difference. Again, red is erosion, blue is well, it's not deposition, it's an outward leaning of the head cut, and white means no change. And the orientation is the same as the photo on the bottom. So that photo kind of shows you the orientation. So the very top there is that red is the grassy area. So one of the things you can see in this difference is there's erosion on the top, there's grass, and there's this leaning forward. And the leaning forward is really interesting. We worried for quite a while about, is that real or not? But luckily, I did get some time-lapse photos that showed a gradual leaning out. And it actually sort of makes sense if you look at this head cut long enough. There are these fracture-bounded slabs of soil, basically, and as they crack, of course, they kind of lean forward. It's just neat to actually observe. So some of the patterns that we were able to see were quite fascinating. So if you look at the top, that's again that same difference that I showed you in the last slide. And then if we move to the bottom difference, so this is the next change. So this is a month after the bottom difference is a month after the top difference. So it's June 9th to July 14th. And what you see is areas that were leaning forward in the top difference, that were leaning out, were the areas of erosion a month later. So that was kind of an interesting pattern. And there's this like line of red. You can sort of see it. My arrow's kind of trying to point to that. There's a line of red that goes across, and that's just kind of right along the rooting depth of some of the grass there. So it's really interesting. You get this preferential erosion right below where the grass is holding in that top layer. So those were a couple of kind of interesting observations. The next thing I did was to look at the probability of erosion. And as far as I know, no one's done this. And I'm really excited about this because I think it's an interesting thing that you can really only do with a data set like terrestrial LiDAR. So each scan, if I break it up into 2 centimeter cells, so I take the point cloud, I do the difference, and I then discretize that from points into pixels. And I use like 2 centimeters. So once I did that, I could look at the probability of erosion in the next survey based on whether it was leaning forward or maybe there was sort of a local depression in the prior survey. So let me kind of walk you through what that actually means or looks like. So this is the topography. This is the head cut. You're looking straight at it here. And if I put sort of a mask on this, a very smooth surface, what you'll see is there are areas that are preferentially kind of leaning out, or maybe I shouldn't say outward leaning. They're just protruding. They're just blocks that sort of protrude a little bit more. And there are areas that are more depressed in this head cut. So what I wanted to do was within each cell, I wanted to give it 2 labels. First, from the prior scan, was it erosional? So it moved backwards. Was it outward motion, or was there no change? And also, in terms of the local area, was it protruding locally from the head cut, or was it depressed? So each cell kind of got one of those categories. And then I could use the thousands of cells to look at the probability. What's the likelihood that it's going to erode if it was protruding outward? Or what's the likelihood that it would erode if it was primarily depressed? Yeah. Yes. Meters. Yeah. Yeah, but it's probably more like 20 centimeters. But yeah, that's what the darkest red is meters. Yep. Yeah, this is why this is actually really, really good landform to measure with LiDAR, because it's a huge signal. So that's another reason why we really wanted to use it. It's not very subtle. So what we ended up seeing in terms of the probability of erosion was that there wasn't a particular difference of erosion if something was locally protruding or depressed. So initially I was depressed. I didn't know what was going on. But I saw that the highest probability of erosion occurred at the apex of this head cut, no matter what. No matter what, if it was protruding, if it was depressed, if it eroded last time, if it was stable last time. Always the highest probability of having erosion was at the apex. And then things started to dawn on me slowly. I started to think about where all the water got routed. So if you kind of look at the photo, all the water gets routed down the apex regardless. There's very few times where water flows over the sides of this head cut. In fact, even when it snows and the snow melts, it kind of channelizes right at that apex. So that's the area where you have the highest moisture. That's where you have the highest pore pressure and the most likelihood of mass failure. So it kind of makes sense that why the apex is always eroding. And if you look at the figure on your left, so the top of that figure, that's looking in plan view. It's a cross section through the data, and that kind of helps to show that primarily most of the movement is along the apex of that head cut, and there's definitely erosion on the sides, but not nearly as much. And then the bottom figure just kind of shows the same thing. So this is actually looking straight at the head cut. So the top there is the top of the head cut. So that's the total change over the 3 years. And total change we see is about 1.5 meters of total erosion over that time period. So again, it was a good place to scan. So the takeaway here from both of these case studies is that I use different methods for uncertainty, different methods for differencing based on the different scenarios. I think that, that's one of the things that we'll always kind of run into with these LiDAR differences, that not the same technique isn't necessarily always the best for every situation. And some of the benefits that I derived were the temporal and spatial contextualization of erosion. So I could see how things were changing in time, how things were changing in space, and I could quantify those to understand the unique processes that are happening in really different systems after wildfire and this gully erosion. But I think the main link between those is the rapidly eroding landscapes, and something like terrestrial LiDAR is really good for measuring things that are moving really quickly. Okay, so I will take any questions.
In this second example
Yeah.
you had, basically there's very little elevation change between the U part pointing to me, on the limbs of the U, and the hinge, as it were.
Yeah, I'll replace hinge with apex.
Apex.
Yeah.
Okay. But there's a gentle overriding slope, so that the apex is slightly upslope.
Yeah.
Okay. That's my only question.
Oh, yeah. Yep, it's just going to keep propagating upslope. But I think the question that we didn't necessarily know, is it going to open up? Is it going to open up wide? Is it going to get really narrow? Is a lot of debris going to accumulate at the bottom? Will it be washed away? Yeah. 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 You're right. That's what my data showed too.
How did you identify Bijou Creek?
Bijou Creek's a really interesting place. So I got to tell you that there are a couple places where people can measure the where the asteroid was that impacted the Earth when dinosaurs went extinct. So it's the Cretaceous Tertiary boundary, and it just so happens that there are a few places on Earth where that are that serve as like there's a special name for it, but it's like a case study or it's like a gold standard to show that. And Bijou Creek just happens to be one of those. So it was found actually by people from the Denver Museum of Nature and Science. They were flying over the plains and looking for somewhere that was incised into the sediment. And they saw all those gullies, and so they went out there. It's a so my advisor teamed up with the people who own that because he was interested in gullies. He knew the gully area was there, and it was owned by this group called the Plains Conservation Center. So it's a refuge. It's a wildlife refuge, and it's a wildlife easement too. So nothing can be done on the land. So that's how we found out about it. But it's a really interesting place. It actually gets some national media. Like it was on Radio Lab, if anyone knows that. Like they talked about West Bijou Creek in that site in particular. They went to see the KT boundary. They stepped over my head cut.
I have a question on your first case study example.
Yeah.
You made your first set of measurements in October and next set in July.
Yeah, there were 2 in October, and then 2 in July.
How much do you have to worry about erosion and effects over the winter?
Yeah, well, I mean that's what we're measuring. So in a sense we're measuring all of the erosion deposition change over time. But I can tell you that having visited the site in the winter, there wasn't much change. There were a few interesting things that happened, and that are kind of incorporated in the net change. Like we saw there was some snow melt, and it created these really tiny rills in a few places. Not everywhere, but a few places it created these small rills. But then they filled back in with sediment, and so you didn't actually. So anyway, the scans. I mean, all we can say is we know what happened at one time. We know what happened in the next time. It incorporates that, but we can sort of apply most of the effect to the thunderstorms. Yeah.
So for the wildfire case, do you? Part of the reason for studying that is to determine if there's actually more chance of hazard after a wildfire. So from your results, can you say if there's going to be more erosion and what the effect of a wildfire landscape is compared to a non-wildfire?
Yeah. I think that, well, we didn't necessarily pair it with a place that was unburned to show that there was no erosion, but there was definitely a lot more erosion than one would expect in an unburned forest. And one of the key takeaways from this research is actually where the erosion was. So a lot of studies have gone out and they use a sediment fence. So they just take a pretty strong tarp and drive in some poles and put it at the bottom of a channel and let everything wash into it. The problem is you don't really know where that's coming from. One of the cool things about that study with wildfires is we could actually show, well, it turns out that most of it's coming from the hill slope. A good portion of it's coming from the channel. But the majority, almost twice as much, comes from the hill slope and these shallow, like 2 centimeter or 2 to 5 centimeter areas of erosion. And that's a really interesting piece that I think be very difficult to see without something like terrestrial LiDAR.
Hey, Francis, does your model for the Headcut, does it take I mean, I'm assuming it takes slope into account, but can you tell us how that head cut changes as it moves forward or backwards forward, I'm going to say, and gets into steeper and steeper terrain?
Yeah, so it's actually really interesting. And there's a range of shapes that you would predict for that head cut. So I did this. I made a computer model to just look at the range of possibilities that would happen. And if you erode upstream faster than you can scour out the material downstream of the head cut, you get this very subtle, this kind of smooth but locally steep area of the channel. And in fact, I see that in some places at that site. There are places where there's more erosion from the face, so it's eroding the face and material sort of accumulating, but there's not enough water to scour it out, and so it just becomes a steep slope. The opposite end of the spectrum is you scour at the base very fast and at a rate that's kind of comparable to the amount that you're shedding material off of the head cut. And that's what you need to be able to propagate that head cut and maintain that discrete step. So it really ends up being highly dependent on vegetation. So if there's this interplay between vegetation regrowth downstream of the head cut and your scour. If you scour faster than vegetation can come up, then you're going to maintain that really steep head skirt. If vegetation grows faster than you can do that, vegetation is hundreds of times harder to erode. And so once it really establishes, it's harder to erode, and then you won't maintain that discrete step. So yeah, it's sort of an interesting story between the competing erosion versus vegetation kind of processes.
So as you change the angle of attack, so as it steepens like this versus the way you have it, which is a very low slope environment right now, I would predict that it will widen as well as propagate upstream.
Yeah, it really all depends on the amount. So I would think that if I was to attack this problem, the way I would probably go about it is I just did a mass failure balance on the head cut, and so your mass failure is basically an interplay between cohesion and your water content in the material. So water content is going to weaken your cohesion, and also the internal angle of failure kind of sets your stability criteria. So it really depends on if the upstream angle provides more water to those sides, which I could see it doing. And then in that case, you're going to trigger your instability criteria because you're adding more water, less slope stability, and so you fail more likely.
Have you followed some of these simulations that Raphael Bras and his students were doing at MIT? So they would take various landforms and then they would sprinkle water randomly, so it wasn't channelized already, and then do things like change the slope angle and the rest, and then try to watch how the landform evolved. So, but I don't think he had good data like you did.
Yeah.
You have. He just had, it was all simulations.
Yeah, that was part of the motivation for the study. 'Cause my advisor came out of that group, and a large motivation was to actually gather like data and in fact use the terrestrial LiDAR to like say, okay, well, how much is it actually moving?
So you mentioned the vegetation regrowth for the second case study, but it seems to me from the photos you showed and the seasonality of those rainstorm events that the vegetation for the first case study would also be a large factor in the amount of erosion, in addition to that boulder cover.
That's true. That's why we actually had to stop the study, because there was so much grass that came up on the site that it was no longer really feasible after 2 years to see the ground and to continue monitoring erosion.
Did you make an effort to try and strip out any of that vegetation at all, or was it too much?
A little bit, but and hopefully you guys can appreciate this, that the technology on this stuff is changing really rapidly. So the last scan I did, actually, I somewhat misled you. I didn't do 5 scans, I did 6. So I actually did another scan that I don't tell anybody about, because there was so much grass that I wasn't really confident that I could see the ground. And at that time, the tools that I used to remove trees, for example, that tree is pretty easy to find, because you can kind of look at the slope around, and if there's a really big change in slope, identify something as a tree. But it was, even the Terra scan, it wasn't that great at removing grass. And so I don't know. I think maybe there are products out there now that people have developed better algorithms to do that. But as of like 2 years ago, there wasn't anything that I found that could really, truly do that very well. Like on that canoe bow that I showed you with the grass hanging over the head cut, that works pretty well because you can really see this like non-grassy area underneath. So it's a very big difference in roughness type, but I think it's different like in a grassy slope. So yeah, I never really had good success on that. But last thing, okay, I did go out after the 2013 floods that happened in September 2013. So I did go out and I said, okay, I can't get the slopes at all. Slopes they're dead to me, but I can do the channel because there's nothing in the channel. And we did do a scan just of the channel, and that was pretty interesting. So I do have some changes due to the channel, and it just got really rocky, and it started to form these, like, they're called step pool sequences. So that was interesting to me from an academic point of view, but maybe not to a lot of other people.
So kind of along the same lines of that, I was kind of curious why you thought there was more erosion in the top of the study area at the 4 mile site than down below where the slopes are steeper.
Well, the reason okay, actually I might have a good slide for that. Let me see if ill prepared. Okay, so that's actually a big part of what I try and say in my paper on this that is in various stages of review. So it turns out that if you map the roughness, so I mapped the roughness on the whole site, and the area at the top is a lot broad. So the distance between the trees is a lot broader, and there is a lot less cobbly and rocky material than downslope. So there's just there's less roughness and less stuff on the ground to break up water as it flows, and so I think that's why there was more erosion. It was just a broader surface, higher distance between trees, and less rocks. I think that's why.